Yo, what's up, everybody? Welcome back. Today we are working on our neural network training framework, and today's goal is to try to speed it up a little bit. So what we are looking at a neural network who's attempting to learn how to predict the orientation of some kind of like wiggly strips, right? So on the fly, we generate a bunch of images at once. We feed them into this thing. We have this red line indicating like the correct answer and the blue line indicating our predicted answer, right? What we do is we run these like image transformations over these things, convolutions. We're making a convolutional neural network, and we can kind of see like, as we run through this stuff, we are applying like some sort of, filtering and like reduction of stuff before feeding it into basically like something that's less human interpretable, but a bunch of like multiply adds with some like activations on these things. Eventually we get to our final answer, and he's going to say, I'm pointing somewhat to the left and somewhat up or something like that, right? This is working okay. We've kind of hand rolled all of this stuff. We've gotten to the point where we will eventually learn something. But we can only have this work with relatively small networks. So let's see if we can find where we set up our stuff. So we set up some convolutions, convolutional layers, we should call them, that basically have like four output channels, and then we take those four output channels and turn them into two input channels with another convolution with like 3x3 kernels. This is like basically nothing. Like this is very little work. Our images are 64 pixels by 64 pixels. This should be like basically immediate, right? And this is enough for our very simple problem. But as we start trying to get into like more complex problems with our neural network training, we're going to have to get more advanced, right? So something that we've been using a little bit for inspiration is YOLO v1, an old paper, but good enough to do like, a real object detection on real images. And if we look at like, what they're doing like, they've got a lot of like, what is this? This is like 56 by 56 by 256. So they're saying, give me 256 outputs for a 56 by 56 image, and do that like a bunch of times, right? So they're running like 3x3 by 256 kernels, 3x3 by 512. Then they're doing, when they get smaller, they get to like a 28 by 28 image pixel with 1,000 output layers, right? So if we try to do something similar, and we just slap like a couple, 256 on here, maybe put one more layer that maps like 256 to 256 again. Is that a thing that they might do? Yeah, sure. That's a thing they might do. And then we'll go down from 256 to 2. My understanding is that this gets like unbearably slow. Right here, we're waiting so long for like one iteration. In fact, it still hasn't finished one iteration. We're still waiting. It's like so slow. And so the question becomes, why? Why is it so slow? I hope that the stream didn't just die because my computer started to lag. So even when we do this, we actually have to reduce the number of input images a lot. And so yeah, the goal for today is try to figure out how to make this not shit. There we go. So with 20 images, 1/10 the images, we finally got through a couple iterations. Yeah, so I want to find out why this is so shit and how we can make it faster. And that's basically it. Let's just start. We'll start by like trying to benchmark some of these things, try to figure out what is taking all this time. And then we can kind of work our way up into fixing it once we know what the problem is. But we have to figure out what the problem is before we design a fix. I assume this is fixable as well, but you never know. Okay. I think stream is like losing its mind. Let's make this problem a little bit less shit. Let's try to make sure that I'm not like using all of my computer's resources. All right, we chilling? Okay. All right, looks like this is successful. So let's try to figure out where the time's going. Okay, so we have some training loop. The training loop is we generate a bunch of data. Hold on, train thread. We generate a bunch of data, then we feed that data through the network. We write down everything that we did as we moved through, right? So we're doing some multiplies, we're doing some adds, we're doing some convolutions. We write all that stuff down, and then we get to the end and we say, how wrong were we? When we figured out how wrong we are, we then can like walk that like chain of stuff backwards and basically say, how much did each of these components contribute to that slowness? Or to that, sorry, that incorrectness. And then once we have like how much everything contributes, we can kind of just like nudge them all in the right direction, right? All of our like parameters, we just kind of like move those a little bit. And so probably we can kind of just, if we throw some logs in here as like a first pass, we can kind of figure out where the time is going. So we have batch generated here. In here we have ran layer this. So here we can have the like layer name probably. Nice. Then here we can say, oh, before we do this though, we have to actually make sure that everything that we've queued to run on the GPU is finished. So we have to do a little flushy every time. This shouldn't be here all the time, but we can, you know, figure it out later how to configure this stuff to run only sometimes. Executor, I think it's like this. We're really going down the chain of shit. Okay, then here we can say, what's going on here? We are calculating the error here, so we can say error calculated. And then here we are calculating gradients. Gradients calculated, and then parameters updated. Let's give it a sec. We should probably put new lines everywhere. Oops. I always forget. And then the other one was in main somewhere. Oh, that one had a new line. Hell yeah. All right. Okay, we need to get a little bit. Let's try to get the numbers up a little bit again, because it's actually going too fast again. I guess what we could do is we could up the number of images. Let's go back to... Fuck it. Fuck it. Let's throw some 256s in there and see if that kind of gets slow again. Okay. So we can see that this guy's getting a little bit stuck at error calculated. That's kind of like the thing that we're seeing here most. And the thing after that is gradients calculated. So we can probably assume that the majority of this time is being spent in calculating gradients. I think that I kind of want something a little bit more advanced here. Like some sort of like timer structure. And we need to make sure that like we can like toggle this thing on and off probably, right? So like because we have to like pause in between segments if we're timing on CPU, and we only want to do that if timing is enabled, probably. So having something like oh shit, chat was broken again. Sorry guys. But yeah, so we should probably have some way to like toggle that on and off. You see Andrew's recent shock, don't forget the flush. Yeah, I did see it. It's pretty good. Pretty good. Google looks much better. Yeah, all I did was move the thing over to the side, and it fixes. It like looks a lot better now. Okay. I'll keep an eye on chat because I don't want it to get lost again. But time to add UX engineer to CV. Hell yeah. So I guess we want like. What do we want? We want like how long did each operation take? And then also we probably want like sub operations probably, right? So like we know that like gradient calculation is taking a long time, but like maybe we want to know how long like each individual segment of gradient calculation is taking. Right, the way that we like do this is like we walk backwards through this tree of events, and like we might want to know how much time we're spending in like each type of operation as well. So like you know, group by which kernel is run, maybe. So like you know, whether or not we're doing like convolution backpropagation or image backpropagation or like fully connected layer backpropagation. All of that stuff I think is probably interesting to keep separately. Yeah. So let's try to make something that does that. You can also time based off of like OpenCL events, which maybe is like a more interesting place to start, where OpenCL itself can say, hey, this thing ran on the GPU for this long, and then we don't have to like inject these finishes everywhere, which is kind of nice. Yeah, maybe let's do that. There's this like a OpenCL profiling mode or something where when you create your like queue of things that you like dispatch onto the GPU, you then say, hey, please enable profiling. And then when you queue a thing to do work, you attach an event for it. And when that event is finished, you can like query it, it seems like, for the start and end of that in some unit. So maybe, yeah, it would be interesting to do like, maybe our OpenCL abstraction guy can have like a with timing, with or like enable profiling, or maybe it's better to do like mode, right? Profiling, not profiling. I wonder if hooking up custom stuff to K-Crash-Grind is easy and what format do they use. That's interesting. Yeah, I don't know. That would be kind of fun though to get like those like those like I really like the K-Cache-Grind initial like the visualization format, the like the cube of cubes, right? You visualize your tree as like actually probably easier to pick up a picture. This shit's so cool. Right? So this like it's like kind of like the each box contains like all of the downstream stuff they use, and then like the bigger the box is, the like more time it's taking. Kind of sick. Kind of sick. Uh Maybe we do this. Boom, boom, profiling mode. And then here we must enable that thing, right? So they said when we create the command queue, we're calling this. Okay, Cashgrin makes me feel like a sick hacker every time I use it. Yeah, hell yeah. One of the things that we can set must be profiling, right? Yeah, here. So we set in queue properties, we set a bit field, which is a combination of the following values. Okay. So hold on. I think that this is one of those things where as one of your parameters, you set like a list of key values, I think. So what is the type of this thing? This. It's kind of like this. And then in here, we set key values. So one of the things is, this is what we're trying to set. And here, his value is enable profiling. Okay. And then there's like usually like an end tag. Properties, a list of properties and their corresponding values. Each property name is immediately followed by the corresponding desired value. The list is terminate with 0. So throw a 0 in here so it knows to stop iterating. Profiler is a tool built by the ChronoScript at Intel. So this isn't like a profiler, really. What we're looking at is just like, literally just like give me times. And then, like if we wanted like an external profiler, I think Leo was asking like, could we hook up to K-Crash-Grind in a way? But I think that we're probably not going to do that. Okay. So here, we probably want like, this we want like profiling properties, and then normal properties is equal to null or something. Can we do something like this maybe? And then here we say like if I guess it's like we switch on profiling mode, and if it's like profiling, we do profiling properties, and non-profiling is normal properties or null properties, I guess. Or maybe we just write null here. Yeah, that's easier. And then here we're like properties like this. And then maybe we actually do this like this, that he's a slice, and then here we write dot pointer here. That feels kind of nice. That feels kind of nice, this build. So here we want to do non-profiling here. And this guy's mad. That's reasonable. And then here we want to do profiling if we're trying to do profiling. Nice. Now this guy's mad. So everywhere in our unit test before where we were doing these before, not profiling. Okay, chill. Is training slow as in the math takes a long time, or the optimizer is so bad that it takes many iterations? Probably both. Probably both. I think we probably might. We'll probably want to take a look at the optimizer at some point. But right now, the math itself is like uber slow. Uber slow. Okay. So I think what we want to do here is if we're in profiling mode, I actually want this to be comp time. Yeah, I almost feel like this shouldn't be like an initialization parameter here, but should be like a like struct parameter almost that like enables like trace, you know. Oh, maybe it's fine. Because like you could do something that's like, you know, timer objects in here, and you could say like, if profiling, then this is like some struct, else void. That's like a thing you can do. But maybe it's fine. Maybe it's fine. We can just not use it if we're not using it. Try to parallel addition to kernel to speed the math up. That's likely going to be where this ends up. In some way. Probably not like as extreme as we were trying to do before, but I mean it's not crazy. It's likely that I assume that the problem is in our like convolution backpropagation. Which is like we're looking at like tons of things at once and trying to like sum them all into one small kernel. But we'll see. So this guy, we want like timers, probably, and what do we want to do here? We want to say like every time we queue a kernel, take a event, add to timer, and then we probably want to like know like which kernels took which times. Yeah. So this is gonna be like a timer, like kernel execution to kernel timers or something. And in here, where kernel is like thing that is running on GPU, not like OS kernel, right? And in here, I guess we can probably just get away with like a flat list of items that have like kernel name and event. I think something like this. And then all we have in here is like items is you know, some array of items. And then every time we queue a kernel, we just push its item in here. So here we'll just say kernel name. An event is this guy. Okay, kernel timers, and we just say self items append. I guess append, we should match names, I guess. And then eventually, when we're like done all of these things, we're gonna like ask for the time spent in each kernel, right? So we're gonna be like, times. And so what's gonna happen here is we're going to probably, like, we're gonna have like many times we've queued up the same kernel, right? And so we probably want to like sum all of those together, right? If we've used the same, because what we're looking for is like which thing do we need to optimize, probably, and this will tell us that. Yeah, so let's sum them all together, I think. So we'll do something like take an allocator to put the response map on, and then we'll do like std auto hash map of, or string hash map. Yeah. And this thing is gonna return what, usize, probably? Probably. And okay, so what were they saying? They were saying that we get this, we call this function on the event. So we go like for self items, we do something like we take the event here, so item event event. We're looking for this. Okay. And looks like this thing is going to be, you know, size of CLU long, start and null. Okay, yeah, right. So we have like var start is here. We pass these guys in like this. So we get start, we get end. I assume these things can fail? What does this return? What does this return? Okay. Return CL success if the function executed successfully and the profile information has been recorded. Otherwise, returns one of the following errors. Okay, cool. So I think we have like CL error here that converts. Yeah. So this just converts from like open CL error to Zig error if necessary. Cool. Do you like a good steak? I actually don't eat meat. Which some people take offense to, which is fun. You go to the bar with your friends and you order a veggie burger and like, what the fuck is wrong with you? It's like, okay, chill, man. I don't know, man. I just don't like eating meat that much. Do you like a good streak? That makes way more sense. Thank you for the tier 1. Much appreciated. Just meat? How about eggs and cheese? I mean, without getting too far into it, I'd prefer not to, but eggs and cheese are hard to give up. They're hard to not eat. They are very good. Yeah, whatever. Okay, so what are we making? We're making like a std string hash map usize. Actually, I guess it's more like ulong, u64. u64, and we initialize this with our allocator. I think that these things actually just got like they just got like deprecated by the standard library in the latest version of Zig, so I guess I should use this. What, you don't like the same food that I do? Heathen. Yeah, yeah. I think it's because like some people think that there's like a moral judgment on them because I don't eat meat. You know? They get a little upset about it, but it's like fine. Doesn't really matter. Okay, I want to do this, and then eventually the formatter will make this look less like shit. And so for each iteration here, we do like ret get or put. We're looking for item name here. And we say if, you know, there wasn't anything, we initialize the key pointer. Which I assume we can just say is equal to this guy without like copying. We're responsible for managing the memory here, but I think that like we're working in a situation where we kind of just leak all of our pointers, and then later, like at the end of each training loop, we like clean them all up at once. So I think it's fine to just like not worry about it. Do we need to dereference this? Yeah, we do. It's kind of like this. And then got value pointer. We initialize this guy to 0 on the first set, and then we plus equals end minus start. Easy. And then we return ret at the end. As long as it's not mushrooms, not when people eat anything. Mushrooms are weird. Yeah, mushrooms are fucking weird. They taste good, but they are fucking weird. I hear that they're like a completely separate like path, like evolutionary path from most plants. And they're like kind of like sentient, kind of like by some definition, by like some fucked up definition. They like talk to each other and shit. Fucking weird. Mushrooms are parasites. They're supposed to eat you. You're not supposed to eat them. Yeah. That lines up with like the stuff I've heard. Okay, so let's put timer here. And this guy, I guess, needs to be initialized. Max elms, I guess, and allocator. And here it's just like turn items is init with alloc and max elms. Easy. Easy. Okay. So this guy, we need like timers equal to try init with, what do we have here? And let's just say like 100. We can't run more than 100 things at once, but you know, whatever. And then this guy, it's an allocator, I guess. Which means everyone's gonna get mad. We can kind of just do this. What about this guy? We just move this down. Easy. Easy peasy. Okay, so does this still like run? Yeah, nothing is going too crazy. Okay, so we need to actually like do something with this. So when we execute kernels, we have to like keep track of them. So I guess here we probably have to like write down our profiling mode. So I guess it's more like profiling info here. Is like a union enum that's like profiling, non-profiling, who holds kernel timers here. And then here we're actually more like timers is, you know, switch on profiling mode, probably. And for profiling, it's like init alloc 100 or something. And if it's non-profiling, we just go non-profiling, simple. Timers is timers, easy. Okay, what's he pissed about? I see. All right. Cool. This guy becomes one of these, and then we should just keep the names consistent. Fuck it. Easy. Easy, easy, easy. Now what's this pissed about? Oh, this is info now. Okay, cool. So now when we're like executing kernels, here, maybe each kernel has a name, which will make someone mad. But that's really easy to fix. Shockingly easy to fix, actually. That's hype. And, now what? It's just like, so Q kernel has an event output. So here, usually we just like pass in null here because we don't actually care about it. But here, now we do care about it if we're in profiling mode. So self-profiling info. If we're in profiling, we create a new... Ooh, interesting. This, like, event pointer needs to live somewhere. Or... Yeah, he needs to live on some, like, allocator now, which is annoying. Which is annoying. That means that this guy needs to take in, like, an allocator. So that we can say, like, alloc... how do we make events here? Oh, we make it here. And then we, like, attach it later. I see. Something like that. So, yeah, if the compiler knows what you're doing and why you're doing it wrong, you should just fucking fix it. Yeah. So here we go, like, event pointer is, like, event. And then here we're, like, non-profiling. He gets, like, null. And then this guy's, like, a event pointer, maybe. And then we pass this guy in here. And then if this thing is used, we like register it with the allocator or our like pool of events. I think it's like this. That way it'll like automatically free himself later. I think that's what we usually do here, yeah. Sure. Sure. And then here we need to, we need to also register this with the timer. So then I guess it's like, if we're profiling, we say like self profiling, this is like timers, append kernel name and the event. Yeah, something like this. Something like this. Cool. And then we have to do this on the tracked side as well. So this is happening here at the same time. Okay, cool. So now these guys are all going to be mad that, like, they need kernels passed in. What's this guy mad about? This guy expected this shit, found this shit. What is the difference? You gotta dereference that, I guess. Why is this guy constant? Because this is constant. So now this has to be mutable, which might cause problems. Yeah, which means, like, this guy has to be mutable. No. Which means this guy has to be a pointer, which means that this guy has to take him by reference. Oh my god, this is going to be a massive pain in the ass. Oopies! Yeah, this is gonna make it all the way up. Lots of mutability fixes. Okay, this guy's mad. What is he pissed about? Expected this, found that. Oh, so true. So true. Wrong type. Okay. Try here. Try here. Allocator goes in here. Add simple profiler. 2879 line diff. Yeah. Allocator here. Easy. Easy. Is this wrong? Pointer. Pointer. Variable, pointer. Variable, pointer. Pointer here, probably. Where the fuck are we? Train notifier? Sure, whatever. Whatever. What's going on here? Math executor. Hold on, this thing doesn't need to be pointer, does it? Why did I change this? I don't think this has to be pointer. Yeah, I don't know. I was smoking crack. Math executor does not. Just the CL executor, which are different things. Ooh, interesting. We need an allocator here. Just slap these guys all over the place. Bump. Bump, bump. Go. If only this wasn't everywhere. Go. We should have just added as a struct parameter, but whatever. Kind of. I mean, it is nicer when you pass these allocators around so that you have, like, indication of who's doing what. But it makes this annoying. But in reality, you know, spending a few minutes doing this isn't the end of the world. It just feels, it always feels way worse than it actually is, right? I bet you if we pull up the timer here, it's like less than 5 minutes of like this bullshit. But you like always want like an automated solution because like it's so mind numbing. I guess what we should do is we should just be like fucking scanning all of these. Record a macro, jump to this, add CL alloc here, and then go again. Go. This one already has one. Has it. This guy didn't. Okay, that should help a lot. Alright. I think we're mostly there. This guy's fixture dot. Alright. We chillin'? We're chillin'. Okay. So now all we should have to do is kind of like at the end of each training loop, we have to be careful to clear this thing now, right? That's like a thing that like we have now that we didn't have before. So I guess that means that our executor, this is like CL zig. We probably want like a checkpoint and restore on this guy now. Or maybe we just have like reset timers. And if he has like these guys, like timers reset or something. Oh. It's, sorry, wrong way. Profiling. Non-profiling does nothing. Okay. And then this guy needs a little reset. Or, yeah, it's fine. So this guy returns nothing, and he's like self items reset. Easy. This should always work. Okay, so now if we run this right now, what we should see happen is that it should start ooming because we didn't reset this thing like we're supposed to. And all we have to do now, that's easy because the is like really aggressive. It happens after like 100 elements. So we should be able to go to like our train thread or whatever. And here, just at the beginning of each iteration, we can do like CL executor reset timers. Easy. So now it looks like we're mostly chilling. And can we then start like looking at this stuff? Yeah, what do we do here? We didn't really make this thing like trivially accessible, huh? I guess here we'll just say like get profiling info, and this will return like a stood string hash map usize like this. Actually, do we want this thing like fucking like sorted? Probably, right? Ah, fuck it, whatever, we'll do this for now. Alright, so here we're like, so switch self if we are in profiling mode, we're like, just return this. And if we're not, then we're like, fuck off. We'll just return an empty bitch. Then here we go, like, get profiling info for each thing here. Var times iterator is times iterator. Okay. While we iterate this thing, we have some entry, and we just debug print that thing. Yeah, nice. Easy. Easy. What is he pissed about? Sure. Dereference the pointer. This guy wants, unmanaged here. This is, like, this thing might fail. Expected some bullshit. Found some other bullshit, which I feel like is actually the same. Oh, this is U64, not usize. My bad. My bad. And then type of this is ignored. Return that. There we go. All right. So we're at the point now. Oh my god, this is lagging the stream so much. Okay, but yeah, can we... How do we make this, like, less fuck up my stream? Maybe it's fine. Maybe it's just, like, a little bit of meme. Does the sound okay when that's happening? Or is it only, like, is, like, I see, like, the video start to lag a bit. But, like, how bad is it? Is it, like, watchable? No response. It's fine. Okay, cool. Then we will leave it. Okay, so can we... Sound is fine, you just look like a fucking robot? Yeah, nice. Okay, cool. That's a good meme. Can we do something like start and end? Maybe we do like a couple new lines here and a couple new lines here, just to make it like easy to identify this thing. All right. So we are definitely seeing some big numbers, some small numbers. This is kind of surprising me. So like, what is the unit of these things? What is the unit of this shit? Start a 64-bit value that describes the current device time counter in nanoseconds when the command identified the event has finished execution. Okay. So can we do like, let's go to milliseconds, right? Stood time ns per millisecond. I've heard in this situation you might optimize the small numbers. Yeah, hell yeah. All right, so what are we looking at? We're looking at the vast majority of these guys are like 0 milliseconds essentially, right? So, you know, if we're talking like 1 millisecond here, we don't really care. It looks like the pain in the ass is everything related to convolutions, right? So forward pass on convolutions is taking, you know, something like 120 milliseconds. Backwards pass here is taking like, that's almost like 700 milliseconds, 620. This one specifically is pretty bad. I would like to temporarily up the number of images again here. just to like kind of like see, does the problem like exacerbated linearly with like number of images or what, you know? Right, so here we went from like, you know, 140, 490-ish. We times our thing by 2.5. So 140 to 316, 140 times 2.5 is like, that's about there. And then what about this like 490 times 2.5, 1225? It is like approximately linear. How does the ReLU grad take more than other stuff? Isn't the ReLU grad there's 0 or 1? Probably because the ReLU gradients are being applied for every single layer, right? So you're seeing just more ReLU grad happening than anything else. You know what I mean? Like, if we look at the layers here, we have 1, 2, 3, 4, 5 ReLUs. We have 3 convolutions, a few fully connected. So ReLU is just going to naturally be like the thing that happens on the most data. Okay. So yeah, I think that it's pretty clear here that the convolution is the pain. And specifically, the back propagation of convolution is like really bad. So can we think about like what's happening here? Let's draw it out. Okay, so we have at the convolution gradient point, we've kind of gone through all of this stuff. We've calculated at the end of our list of shit, we say, how wrong was this sample? So we maybe have like, you know, 50 samples of things that we're trying to predict. And so we end up with like 50 numbers of like incorrectness, right? Wrong times 50. Each of these wrongs came from like a bunch of linear connected layers, blah, 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 linear connected layers. And like kind of at each of these points, we kind of figure out like this neuron contributed this wrong by this amount. This neuron contributed by this amount. This neuron contributed by this amount. And then eventually we get to the point where one of these neurons is connected to every single pixel in one of our convolution outputs, right? Which means that we have like an image kind of that is like for each pixel, how does each pixel contribute to incorrectness? And so if we're trying to figure out how an image kernel contributes to the incorrectness of this pixel, we are basically saying this kernel touched every pixel in the input, right? We took this box and we like multiplied the numbers in the box by adjacent pixels in the image. And this kernel touches every single pixel. So I assume that what we're doing stupid is we are just saying we're probably doing like 50 images times 64 pixels wide times 64 pixels tall. We're doing like this many operations per thing that we're looking at in the output here, which is like super like not parallelized. And probably we can just do something like do each image at once, like do all 50 images together and then like fold that answer down at the end to try to like use more GPU bandwidth. Because like what we're doing here is like we calculate like for this kernel, how much did this pixel contribute to like the final, this like element in the kernel? How much does he contribute to like the downstream incorrectness, right? And he is like in one thread on the GPU summing every single pixel in every single image, essentially, probably. And I assume we just don't have to do that. So can we look at this? So somewhere we have conv many grad kernel. Ah, shit. Fix me. This whole thing can probably be done by using gradients as a kernel that is run over the input image. Yeah, true. But that's okay. So here we can look here. We have image loop, y loop, X loop. So I assume what we could do is just like do more work at once. More work at once. So if we just delete this outer loop here, then we'll be going like for y for x. And in reality, we could probably delete each of these loops as well. We could probably like first do, right? Because all we're doing at the end of this is summing everything. So there's probably something here. But yeah, I think that what we just do is we just delete this loop and we do a second pass to sum all of the outputs of our images. Probably. So we call this like pass 1. And when we call this pass 2. And so we have to think about like what are we doing here? So we are creating. So we have what? We have many output images, right? Many of these guys. And each of these guys has like how much his incorrectness contributes to the final answer. So somewhere here, before we were saying that we have a kernel that is of this shape. He's like kind of like a 3D box. And we were running once per cell in this box. Right, whatever. And what we want to do now is run per cell in this box per image, right? So like for each of these images now, we'll like create a new box. And then at the end, we flatten like this box down, right? So we like sum the things where in this corner of every box, we like sum those into one final box, I guess is what we're looking for. Cool. So what's going on here? Is n here number of images? Yes. Okay. So we change this guy to say queue up way more. Math executor. So we're on conv many grad. So first of all, we're gonna have 2 passes of this kernel now. So this is like conv many grad kernel pass 1 and pass 2. Okay. These guys get saved somewhere, so conv many grad kernel pass 1 and 2. These guys are like pass 1, pass 1, pass 2, pass 2. Okay. So now when we use this guy, this becomes pass 1, and this guy is going to run for times the number of images. So this is going to be like the most outer dimension. Yeah. Cool. Yeah, here we go. So pass 1 creates 1 output, 1 kernel gradient per image. Pass 2 folds those into 1 answer. Into, yeah. 1 kernel grade, 1. Yeah. Fold each kernel down. Okay. Cool. Cool. So pass one here. We are going to delete this outer loop, basically, and we just calculate image index is global ID. What is happening here? So here we have kernel size. Ah, fuck. I have to remember my, like, multi-dimensional indexing shit. So this is 1, 2, 3 dimensions many times, right? Once per image. So we want our image index is like global ID mod kernel size. What is kernel size here? Kernel channel size times in channels. That feels right. So this is like kernel width, kernel height, kernel width, and this is kernel depth is like in channels. Okay. So why is output channel the same here? Oh, because already though, we had 4 dimensions of input already. Because we're running this for like many kernels already. Right? So this is kind of like each kernel creates like one output channel. So we need to do this many times. Right? So we're creating. Yeah. Does that make sense? So before we were running this B gradient dims. So like what is a kernel look like? Kernel dims is 4-dimensional. Yes. And so we're adding a 5th dimension to this thing. I see. So output of pass 1. I guess we write this down here. Out grad. We throw an n here. Yes. Yes. Okay. Which means that this guy has to be like, we need another thing here, which is like kernel block size or something. So this is like, I don't know. Well, I don't know how to like explain this better. This is like kernel size is like 1 kernel for 1 output channel. Kernel block size is all kernels for 1 output image. Yeah, something like that. Something like that. And then now we do a little bit of this. So this is like percent kernel block size over kernel size, and this is image indexes over kernel block size. Something like this? Something like this. And then we should just be able to like delete this outer for loop now because we have an image index that is like fixed for this run of the kernel. Okay. And then pass 2, what are we taking? We have like pass 1 output. We have out, right? And then we need all of width, height, in, out, n, right? And we're trying to be like, input is width, height, in, c, out, c, n, and output is this without the n, right? So all we have to do here is we say, what we have like our global ID is get global ID 0, if global ID is greater than or equal to width times height times in C times out C, we return. And then we're going to be doing like out at global ID is equal to something, like some sum, right? And here we're going to be like for image index equals 0, image index is less than n. You know, something like this. We say like float sum equals 0, and we say sum plus equals whatever, right? So we're going to be looking at like, I guess here we have our kernel index x is going to be global ID percent kernel width, which means that here, that means we also need like, oh, this is k here. Our ky is, well, this is like width by height by channel, right? So you have like this stuff linear in memory, followed by this stuff, followed by this stuff. So your height here is divide by width, and this is going to be like repeat for every channel, right? So it's like kernel channel size is width times k height. We say global ID percent kernel channel size here, and then we divide this by kernel width. Okay. Then we just keep going up the chain here. So kernel in channel here is kernel size over kernel channel size, and then out channel is global ID over kernel size. Yep. Okay, we're getting somewhere. So this is kernel channel size times in channels. Okay. Cool. So now when we're indexing this thing, we do like, I guess we have kernel block size as well. Here as well. So this is kernel size times outc. Okay. We should have written down, did we not write down the fucking indexes here? Okay, we did. Okay, so here, I guess we're saying, we have like a constant offset. Kernel block offs, I guess. This is gonna be like, I guess actually we don't need all this. Right? This is just like our global ID modulo the kernel block size. And then we just add this every time, right? So we just say like kernel block size times image index plus kernel block offset. Yes, 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 yes. Yeah, which means that all of this kind of goes away. And we can kind of calculate kernel block size here is width times height times in C times out C. Height. Yeah. Then this is above kernel block size. Bang, bang, boom. This stuff all goes away, and this becomes really straightforward. I think that's right. Maybe. I'm not like 100% against this being it. So if we did this right, then we just have to like set up our inputs this guy. So when we call this guy, it's in math executor. Conv many grad here, when he does a second pass. Okay. So first of all, this guy's not going to be using b grad here. He is going to be using b grad pass 1, which is of shape. Hold on. So it's like, I guess it's like this. We just do b grad dims 0, 1, 2, 3, and then huck in an extra one at the end, which is the downstream gradients like this. Right? I think it's something like this. So we have our kernel width, height, in channels, out channels, n. Cool. Cool. And then here we can just use b grad pass 1 num lms. And then we have to execute the second pass now. Right? So we're like run pass 2. And on pass 2, this is b pass 1 n, I guess. And we have b pass 2 n is going to be the output gradients of the whole thing. Okay, yup. Hell yeah. And then here, this guy's using b grad pass 1 output. Then we're taking, what is it? It's kernel width, kernel height, in channels, out channels, and then n. So really here we could just be using like b pass 1, boom, 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 1, 2, 3, 4. Okay, and then we have an input and output. So our input is b grad pass 1 output, and our output is b grad output. That's like a maybe. That's a maybe. We need to check if it's right, so we should probably just run our test. And if they're working, then we're looking pretty good. Okay. We're waiting. Building suspense. Conv many 2. Okay, so the gradients here did not work. So we did something fucking stupid. Great. So now we have to debug. Now we have to debug. Okay. So what did we do? What did we even do? Lots of changes. Okay, here. So we create a new tensor. We replace the output hype. Okay. Then we run pass 2. Nothing crazy there. Then in terms of like the OpenCL changes, we just added kernel block size, which feels right there. Just did a bunch of unindents, I think. Yeah, so we just took out the for loop there, and then we did the sum. Okay, cool. Cool. So I guess we just have to figure out where we're going wrong then, because clearly we're doing something stupid. I just don't know what it is yet. So can we maybe start, I guess we have to start logging somewhere. First of all, let's update our build here to, only run conv many grad or whatever. Just to make it so that this is a little quicker. A little quicker to test. All one test pass. Whoa. What the fuck? Oh, it's called conv many 2 maybe is the one that we're trying to test. Let's double check here. Conv many 2 is running gradient tests. Okay. This time? Fail? Fail. There we go. Okay. Okay. So, what the fuck do we do here? We need to test some. We need to log somewhere something. I don't know what yet. I guess let's just log that all of the things that we think should be happening are happening, right? So can we check if so let's actually look at the test, I guess. So this is loading from some JSON. We like generate a bunch of like convolutions from PyTorch and Python land, use those as like inputs to the test somehow, if I remember correctly. And then yeah, we like validate that we get the same answer as PyTorch. So what are we outputting? We are outputting a kernel. So we have 4 images, 2 channel. Then we generate kernels with 3 outputs. 3 by 2 by 3 by 5. This is our like kernel size. Okay, so our images are 4 wide. So here we should be able to see like if global ID percent kernel block size equals 0, can we print out the image index here? So what we should see is we should see 0, 1, 2, 3 or something. Right? That's what we should see? 0, 1, 2, 3? Which seems bad. We're only seeing 0, 1. Yeah, that seems bad. That would explain something. I would like to double check as well that this is what we're seeing. So can we downstream grad shape should be downstream grad dims here. Yeah, so this is 4 images. Our dimensions are like backwards, but we do see 4 images here, and we're only looking at 2 of them, which seems fucking bad. Seems fucking bad. Are we exiting out too early? Yeah. Oh, no, sorry, that's pass 2. So in pass 1, what is our, like, exit condition here? Yeah, we're making a mistake here. Okay, let's try this. Let's try this. Okay, 0, 1, 2, 3. That's good. We are at least seeing us attempt to go through all 4 images. We are seeing nans, though, which seems kind of fucking bad. So, let's also print the sum here, maybe? Let's see if just like the first guy is an nan. No, okay, so these guys are like maybe okay. Can we say more like if sum is equal, if is nan sum, can we printf maybe our index here? So can we just be like 1, 2, 3, 4, 5, right? We want kernel X, kernel Y, kernel like input channel, output channel, and N, or image index, I guess. That's kind of what we're looking for. They might want %use there, not %ds, because like signed versus unsigned shit. Okay, so maybe we're just not nanning here. So can we then do the same shit here? Maybe this is just offset. Okay, let's see. Okay, so we're not seeing any logs here either, which is interesting, which means that we must not be like outputting everything. Right, there must just be like some elements that we're not outputting by mistake here. But I don't really know what that would be. Can we just print global ID here? What the fuck is going on, man? What the fuck is going on? So here it looks like we are getting all the way up to 63, which is that high enough, right? We got to check that. So in here, let's print out kernel shape. Right? So is this guy supposed to be 64? Maybe. Our kernel shape is 5 by 3 by 2 by 3. 5 times 3 times 2 times 3. 90. This guy's getting up to, actually 89 here, we see. Interesting. Also, we're not seeing nans this time, but we are seeing maybe inconsistency in the value that's coming out, right? Which really indicates uninitialized memory. I would love to maybe check that we're outputting the amount of stuff we expect to be. So how do we do that? How do we check that? 0, 1, 2, 3, 4. Okay, so let's make sure that this is right. B pass 1 dims is this. B grad pass 1 dims. What does this guy look like? What's he look like? Dude, Quipperin? Thank you for the prime. Much appreciated. Are you comparing against a PyTorch person? Partially. Partially. So, B pass 1 dims, 5 by 3 by 2 by 3 by 4. Great. That makes sense. This matches the kernel shape plus the number of images that we're looking at. Yeah, so like the final answer is based off what PyTorch gave us. Yes. Okay. Then can we, it'd be interesting maybe to like create tensor filled here. And can we fill this shit with nans up front just to like really fuck shit up? You know? Because then we can maybe get like, we can see whose memory is being used uninitialized, right? We're seeing nan here now, which is interesting, right? It means that we must not be outputting for every single element in this initial pass. It's gotta be, right? It's gotta be. Bash Bunny, thank you for the big raid. What is up, you guys? Welcome, welcome. Can we give you guys some context really quick? Maybe. If we stash here, we should be able to build this guy and show you what we're working on. we are working on our neural network training framework, right? So we are building something that, eventually, I guess for like Uber context, eventually I'm working on like a meal tracking website. Right? And one of the things that I want this guy to do is like, as I eat stuff, I like, write down how much of everything that I used. And maybe I want to know like, do I have like what should I make today? Well, it depends on what's in the fridge, right? And so it would be nice if like it knew all the stuff that I've made and all the stuff that's in the fridge, and it could tell me, hey, I could make mushy rice today, or milk rice, or puke dip. You have all of the things in your fridge to eat this thing that you've eaten before. And so to do that, we kind of need to like track how much of like each ingredient we have, which we have like most of implemented, right? Because like if I'm making, a burrito, as part of making the burrito, I write down all of the stuff I use, which means that if I just knew the initial state of the ingredients in my fridge, I would know how much is left, and I know how much I used when I made burrito last time, and that like gives me all of the information I need, right? So I don't want to like manually type in the amount of stuff when I load into my fridge. That's a pain in the ass. I already hate getting groceries. Why make it worse for myself? So instead, what if I use my phone to scan the barcodes of things as I put them in the fridge, and then it knows how big everything is. Right? He knows that like this barcode is a 2-liter jug of milk, right? So we went through like this kind of like saga a little bit of trying to like detect these things manually, right? Kind of scan these barcodes with like hand rolled stuff, and we got like we got fairly far. It would like kind of works, but there's a lot of like edge cases here that make this like kind of hard, right? This milk carton, if you were to just do like a one-dimensional scan line across this thing, there's like you're missing information, right? Because of all of these like occlusions of the barcode. So what you really need to do is you need to do some sort of like 2D processing of this thing to like kind of like approximate, hey, I think there's a bar here. And so we tried a little bit. It was just getting like slightly difficult, and we're like, you know what, fuck this. Instead of like trying to handle like blurry barcodes and like mirrors that are like, on aluminum cans, and like lighting problems and all of this stuff, what if like a neural network could just like learn what types of things are part of a barcode for us? And so obviously, because we don't use dependencies around here, ew, gross. We started writing our own neural network training framework from scratch. And so that's kind of what we're looking at right now, is we have like a neural network training thing that can look at the orientation of these bars that kind of represent barcodes a little bit. We're not quite there yet. And eventually he kind of learns to like put the blue line up with the red line, right? To kind of like match the orientation of the bars. And what we're working on today is as we try to get into like more complex situations with like deeper neural networks, it starts to get like really slow. So we're working on the idea of speeding up calculation of gradients. So the way that this thing trains is hand wavy. You like give it, you do a bunch of math, you write down all the math that you did, you say, I multiplied these two numbers together, I added these two numbers together, I like did like a convolution on this thing where I like take a box and I like slide it over a picture, and that box like does some mathematical operations and like produces like the output pixel that matches the input at that spot. We write all that down, and at the end we go, how wrong were we? Well, now that we've written everything down, we can kind of like say how much each individual parameter of this like nest of shit that we did, how much does that number contribute to the incorrectness at the end? And you kind of like punch it in that direction. And so yeah, we are working on the fact that like some of that is slow, hand wavy. So thank you, Bash Money, for the raid, much appreciated. Apologies for like maybe not like the perfect context there, but hopefully it's enough. So I think there is some computer vision mask way of solving this, for sure. I don't think that we're doing the smartest thing, or even like the best thing. A lot of this is like an excuse to explore ideas, right? So writing a neural network framework is like funny and fun. And so that's kind of like the main goal, and then like the barcode scanner part is like secondary. Yeah, so what we've determined so far is that when we take like input image and run like these like boxes over the input image. And each box will like learn a different thing about the output. And so like what happens is you put the box here, then you put the box here, then you put the box here, then you put the box here, you put the box here. You do a bunch of like multiply adds. And funny and fun, bro, we've been on this for the last 2 months. It's fun. It's fun. I'm having fun. It's fun. So like for each pixel, we are kind of like, this pixel is influenced by the box at this location. This pixel is influenced by the box at this location. This pixel is influenced by the box at this position, right? And so if we say this pixel in this picture, is this pixel contributes to like the incorrectness by some amount. Every pixel in here contributes to the incorrectness, and like every single pixel in every single image that we're processing is like somewhat influenced by one of these kernel parameters. And so what we're trying to do is we're trying to like split out on GPU, when we're going backwards, we want to basically calculate the incorrectness in our box here for every image, and then sum all of the incorrectnesses at the end. And that's what we're trying to split out right now. And we are having a little bit of trouble there. Where it looks like we're using some uninitialized memory somewhere. And so that's kind of what we were debugging when you guys raided. So, oh shit. So thank you so much for the raid. I think we're just going to jump back in. But I hope you guys had fun over on Bash Bunny's stream, and I hope you guys have fun here. Okay. So we're spamming because we're running the wrong thing. That's why. We're running our unit tests. So we have proven that if we take our initial tensor and we fill in with nans, we get nans later, which is bad. Our first pass here should overwrite every single nan that we wrote in at the beginning. What's OpenCL? OpenCL is like a open specification for ways of running arbitrary compute on parallel devices. So like, I don't know if you've heard of like CUDA before, but it's like you take like a chunk of C code, you run it, you compile it for like a GPU, and then the GPU will like run that chunk of C code like 1,000,000 times at once. And so OpenCL is kind of like the cross-platform way of doing that. It's the opposite of closed CL. Thank you. Okay, conv.cl. So I guess what we need to do is figure out why this guy is not writing out every time. So here he should be saying, I have been executed by the GPU queuing system 1 time per input. So can we check what number that is? Size is b past 1n. Cool. Width, height, kernel width, kernel height. Kernel in, okay. 0, 1, 2, 3, 0, 1, 3. I think that's right. Okay, let's just see. Okay, so we are saying that the output here is 5 times 3 times 2 times 3 times 4. 360. So we're running this 360 times in parallel right now, which should be fine. Okay, so then what we want to do is we want to check which guys he actually outputs, I guess, right? So outputting to this guy. Global ID. So each thread on GPU, what we're hoping to see is outputting to 360 somewhere in here. And we're kind of seeing him clamp at like, what's the highest number in here? 179 maybe is the biggest number I see in here. Yeah, so that does seem like the bug. So why is he not doing anything? It must be this. Kernel block size times n. Can we do this? Printf If global ID is 0, so we only print this once, printf, you know, can we print kernel width, kernel height, in C, output channels, and N? This is the dimensions, and then the final answer. So kernel width, kernel height, in C, out C, N, and then kernel block size times N. What is going on here? 179 is almost half. That is a good point. So here's what we're seeing. 5 times 3 times 2 times 3 times 4. 180. Am I fucking stupid? 5 times 3 times 2 times 3 times 4. 360. What? This is the wrong thing. Kernel size here, not kernel block size, not kernel channel size. God damn it. 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 Okay. So we should start seeing this guy now. Output up to 360. Huge for us. That is so big. Test pass now. So I just fucking fucked it up. As per usual, just a little... It's so easy to accidentally write channel here instead of kernel size. It's because I copy pasted this line like a fucking dumbass. We don't like, no copy pasting allowed. Okay, so now the question is, first let's like run all of our tests again, just to make sure that we're not like out to lunch. And I guess we can try running this thing again and seeing if we're like significantly faster. Right, so, fuck. We still have those global IDs printing. Global ID colon. Get this shit out of there. Okay, give him a sec. We gotta build suspense, run all of our tests. I think what we should do is, we could like make this like way faster if we shared like an OpenGL or an OpenCL executor between, but whatever. We forgot a couple more here. Debug print, debug print. Oh, but these are just in the test, so it's fine. It doesn't matter. Is there debug prints in here? Yes, get these out of here. And then otherwise, we should be chill now. Okay, so let's run our training now. And is this better? Shockingly, not that much better. I think before we were seeing like 1200 milliseconds, and now we're seeing 1080. We should have fucking committed before we made these changes so it was easy to compare. We can probably do that. Let's do a little bisect. So patch add everything that's related to our profiling stuff. Profiling, 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 profiling. All of this is related. Profiling, profiling, profiling. What's in here? Profiling. That was profiling. This, some of this was not. This was profiling related, I think. So was this. Ooh, this is not technically related. This all looks profiling related to me. Yup. Okay. All of this was as well. This was not. This was the fix. This was also the fix. Profiling, 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 profiling. Lots of refactor, 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 refactor. One more. Oh, fuck. No, wait, that's fine. Profiling. This is not. This is actual changes. So no, no. Yes. Yes. No here, no here, no here, no here. A bunch of yeses. What's this? What is this? Oh, we do not want that change. That's bad. We don't want any of this. Okay, there we go. Okay, so this should be profiling stuff. And if we stash, hopefully this builds. It does not. So we're gonna have to fix that in a second. But let's commit the rest as the rest. And do a little rebase. And edit this and try to make it compile. So we just accidentally pulled in too many changes when we did this, when we were flipping through. I don't actually know where though. Here. What is he mad about? Ah, we accidentally took a change here on like struct parameters that we don't want. But then are we chilling? And then somewhere this guy didn't get a change because we changed him for multiple purposes. Okay, but we're still back. Okay. So this shit is like this, and then get rebase continue, and then here I guess we just say go to whatever the fuck you were trying to do completely. Take all changes from here. Just make sure that this looks kind of right, yeah. And then let's try to get I don't know. Let's try to get the rest in, but kind of split out by things that we care and don't care about. So this is like making the model bigger to like make it perform like shit. This stuff is not that. This stuff is the fix. This is the fix. This is the fix. And then this is just like stuff we don't want completely. Okay. So make slow. And then check out again, take the fix. Here is the fix, the fix, the fix. This is the part of the fix. This is part of the fix. This is not, this is not. The fix. Okay. I've been using Jujitsu instead of Git recently. Pretty good, and you can use it with existing Git repos so that people can't even tell. Yeah, I guess like this is shit. Okay. So we should be able to go back to make slow now. And see what our stats were saying here. Fuck. I think we didn't have profiling on right now, maybe? No? Why does this not work? I feel like this should work. So here he's saying, we can't get the profiling info. Oh, because we need to finish before we pull, we need to make sure that the, this guy has finished actually running before we try to pull the times out, that's why. No? Surprising. Oh. This line goes above, not below. Oopies. Oopies. All right, here we go. Yeah, so here we're looking at like 1284. Uh-oh. Is sound okay? Looks like it. Just the video gets kind of fucked. So 1227. Can we do check out whip, get status. I think that we have a change in here. Yes. Get commit -m fix up, get rebase a little bit back, throw this into the profiling stuff, and then check out the fix. And so we need to write this number down. We were looking at this. This is the prefix. Prefix numbers. Prefix numbers. Okay. Now here, is it much better? This is postfix. Hello. So here we've basically gone from 1227 here to 1069. So we've saved off a little bit, but not as much as I was hoping for, which is interesting. I was expecting this to be way better. So it does look like the second pass here of summing over number of images is like basically no time, not worth talking about. Does OpenSale have any optimization flags you could pass to the compiler like O3? That's a good question. Not really sure. But I would hope that it's being optimized a lot by default, but that is a good question. So I would expect that this should be okay. So this is still summing for each kernel output over each row and column. So I guess we could just do 3 passes, right? We could just kind of like do this again. Right? So here we split over image. We could split over row as well, because he's still doing row by column per thread here. But we should be able to increase the number of images without much cost, right? Because we should be able to get a lot more images without much cost, I think, because we're now like parallelizing every image. So if we go 100 here, does that like grow by that much? That's the question we should ask ourselves. Uh-oh. Yes. So that's surprising to me. This is surprising because we're supposed to be parallelizing over number of images now. So this is kind of indicating that we might actually be at GPU capacity. Because I kind of assumed that like you could just do more images at once and we would like have more things queued at the same time. Because like surely there's enough. But maybe the number of things that I can do on my GPU is like not that high. Monitor it. Yeah, I think Radeon Top, which is what I've used in the past, is broken on my GPU, on my like current computer. Maybe if oh, you know what? I think it broke when I changed my CPU from Intel to AMD. So maybe Radeon Top here needs me to tell it which bus to look at. Yes, I bet you that's it. LSPCI maybe? Hold on. We can get there. We can get there. You can pair flops with your theoretical max limit. Yeah, true. But I think we can actually just check here. LSPCI. So which PCI bus is like my real GPU on? Is the first number the bus? Probably, right? So bus 6? Radeon Top. Can I like bus 12, he said. Is it the second number? Or are these hex? Oh yeah, they are. So I want 12 in hex is 16 plus 2 is 18. No? Oh, also, kernel too old, but like it used to work. I think it is when I switched Radeon Top select GPU. I'm pretty sure it's because I have like an integrated GPU now in my CPU. And bus IDs are 1 and 2. Yeah, that's what I thought. Grep VGA. Oh, I guess this is what I want. B3. There we go. We're so back, baby. So we can kind of check here. We are just saturated. That blows. I assumed that wasn't the problem. That's quite surprising to me. That's quite surprising. Interesting. So that means that we don't just have to go wider, which was my initial thought. We just actually have to be better. Fuck. Okay. Interesting. Interesting. I just made an assumption and made an ass of you and me. So, I guess we have, at some point we identified why it was slow. Conv backprop. Now we want to know, we tried fixing like parallelize grad more. This was no go. So now we have to come up with another option. So let me think. Let's think. So this gradient, we know that this is going over, this is just like an expensive operation, right? We are doing each kernel. Can we just like run some numbers here? So we have convolutional layers here. This is 256 kernels. Okay, so this guy in particular is quite egregious, right? We are saying, run me a 3x3 kernel over something. So this is 3 width, 3 height, 256 depth. This is like the size of our kernel. And we have 128 of these. Then each of these is running over 50 images, right? 50 images? 100 images here, right? 100 images of 64 by 64 size, right? So when we get to the backprop layer here, we're going to be looking at every single pixel in every single one of these images for every single box pixel channel, right? So this is actually like number of things that we have to do here is 3 times 3 times 256 times 128 times 100 times 64 times 64. This is like the number of things that we're doing at once, right? So what is that answer? Do I really not fuck with Python? God damn it. Copy Python 3, paste. Holy fuck, that's big. That is a big fucking number. How many digits is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 120 billion fucking outputs. Wow, I really underestimated the expense here. Dude, that's crazy. 120 bill? What is my like floating point operations per second on this thing? 6700 XT gigaflops. Is this something that I can like look at? Do they have like a little hit me with flops? Peak single precision performance? 13 teraflops? That's like a lot higher. That's like a lot bigger. This is like 120 gigaflops. If, I mean, assuming that we're doing one floating point operation per. But like then again, maybe you're like 10xing for like, or not even, this would be 100 times, if we were doing one floating point operation per, which we're probably not. Which is fair. So then like we might be hitting like memory performance limits or something. Yeah, I guess like within the kernel, we're definitely not doing like contiguous looks, which is interesting. Yeah, how many operations are we doing per thing here? Just like back of the napkin math here. It's not 0, I'll tell you. It's not 1, I'll tell you that much. A conv 3x3 is 17 flops, right? I think. 1, 2, 3, 4, 5. You have like multiply times 9, then a sum. I would think a conv 3x3 is 10. I would think. Do you need a depth of 256? I don't think so. Right? I don't think so, but I think that it like, you know, people do it. Like I was looking at like a relatively simple network, YOLO V1, and they got tons of like 56 by 56 by 256. Like they've got tons of those in here, and I would have hoped that I could train something like relatively this 9 multiplies and 8 adds, I think. Oh yeah, you do have to add every one. You're right, my bad. I was thinking like 9 multiplications plus 1 sum, but you're right, it's 9 plus 8. You're right. Um yeah, so like for each output here, we're doing like, I mean, we can kind of like count them. This is like 3, 6, probably like another 10 in here. I guess these are like uint ops, but whatever. They're probably like similar. These like, yeah, we're doing like a fair amount. Maybe like a 10, you know, throwing in like 50 things per iteration here isn't crazy. Only like a couple floating point operations, I guess. A lot of this is like integer arithmetic, but I don't really know what the cost of that is. YOLO isn't simple as state of the art for some time. Maybe, okay, I might be making like an unfair assumption. It didn't look that, like, conceptually it doesn't look that bad to me. But yeah, maybe, like, yeah, we could look up, like, how did they train this thing? Uh, I want to know, like, what they trained on. Do they tell us? Do they tell us? Um, Training. Oh, so they started off ImageNet, sure. And then do they talk about, like, how much time this took? Not really. I'm not seeing anything jumping out at like, we used this many GPUs. All right, sure. Because like, why would you? Why would you say that? Okay, fine. Maybe the conclusion here is that the answer is just to do less, which we can very much do, right? Like, we very much do. We really need like 64 by 64 by 256? Maybe that's insane. Maybe that's crazy. So maybe we just try to get like down to less pixels as fast as fucking possible and go from there. Throw it into LLVM MCA. What the fuck is that? Machine code analyzer. I don't even know, but like, what I'm doing isn't necessarily even like CPU side, right? I don't even know if like what I'm doing is going through LLVM. It's probably not, right? OpenCL kernel, I guess. Yeah, I think like CL info will tell me. I think I'm using like AMD's proprietary OpenCL drivers. So I don't even think that I'm going through like anything LLVM-y. YOLO V1 can be trained on one GPU apparently. That was kind of like what I assumed, but maybe it still takes a long time. Because like again, like this is just like doing the math, like 120 billion things, like outputs per convolution. is just a lot. It's a lot. So, anyways, I'm pretty sure it goes. Basically goes through LLVM on AMD. I'm pretty sure that it goes through LLVM. Yeah, I'm not sure about the proprietary drivers, but they might. They might. Yeah, but it's time. You train for like 2-3 minutes at most. They probably run for like 24 hours. God knows. They're probably longer. Probably longer. Yeah. Okay. I guess I'll think about it. I'll think about it. The answer might just be that we can't do it. That'd be okay. I should probably at some point try to compare to PyTorch as well. I don't know if I can like run with my GPU on PyTorch very well. Last time it was a pain in the ass, but it might be worth a shot. Then we kind of know like the upper bound here. But okay. Okay, it was worth a shot. I think we call it there while I think about what to do next. Thanks for watching, guys. Reduce layer size. No, yeah, that's probably going to be the play. Probably. Okay, thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 Pacific time to 4 o'clock Pacific time. You know, usually it is 2:45 now, but today was a short day. So we're working on this like neural network stuff. We have a lot of other stuff in the backlog. Like if you check the YouTube, like operating system development, terminal emulator, maps, like GPU from scratch, like virtualizing a GPU stuff. There's all sorts of stuff in there if you want to check it out. We post, you know, most feature development goes on the YouTube, but like some stuff like refactoring and stuff does not. If you want access to VODs of all of the streams, there, you know, you can subscribe to the Patreon or join on YouTube members or sub on Twitch. You get access to the VODs and knowledge that you're helping the stream continue. I think that's all. YouTube, peace out, and Twitch, let's find someone to raid.